Alright, so we're going to start off with a real quick break-even derivation, i.e. the derivation of the break-even formula. And so it all starts with the definition of expected value, or EV, over here, which is just the stuff that you win, your reward, times the amount of times that you win it, or the percentage you win, minus the risk that you lose, times the amount of times that you lose. And by the way, I got rid of the percentage symbol just because to clean things up. And I want you to notice that every time that you lose, you're also you're not winning. So basically, they're the opposite of each other. And because they're a percentage, we can just write 1 minus to show that they're opposite. And that way, we get rid of this second variable L. All right, and the next step is we just distribute. So risk and here. Now this first one is negative risk, and the negative times the negative becomes positive. Okay, really easy. Then we factor out the W, move risk to the other side, and we divide by reward risk on both sides. Alright, hopefully that's not too new. So this is the formula for break-even win rate. And so what this means is, let's say you are risking 2 to win 5. Well, we throw it into the formula, which I guess I'll just keep this W. So we're risking 2. And the reward is 5. So if we throw this into the formula, we get 2 7. So this means that we need to be at least 29% sure that we're winning this 5 rather than losing this 2 to make this a break even. So if we win 30% of the time, then all of a sudden in the long term we're making money, or we're winning. We're winning more. Our expected value is going to be a little bit above 0. Alright, so now we're going to take a look at break-even and the formula in the context of Among Us. So let's just look at a common scenario, which is that there are 2 imposters, 10 players. The round starts. 2 of them have been killed in the meantime. Somebody reports the body. So we are left with 2 imposters among the 8 survivors, which means 6 of them are crew, and again, 2 of them are imposters. So if we vote out right now, right, and we vote accidentally one of the crew, we lose 1 crew out of the 6 that we have, right? But if we vote and we vote correct, we vote an imposter, we vote out one of the 2 imposters. And if it wasn't clear already, crew are 3 times less scarce than imposters are. So imposters are a lot more valuable, you could say. So our reward is 1/2 and our risk is 1/6. And so if we plug this into the formula, we get 25%, meaning that we need to be at least 25% sure of one of these people being an imposter. Yeah. So I was pretty shocked when I, just plugged in these numbers, and I was like, wow, when you see YouTubers, they don't vote that much. For example, in these rounds, you often hear people skip, or just people say skip if they're not sure. But mathematically, I thought I had just shown that was the wrong play. So I thought about it a little more, and the problem with this thinking is this right here, is this risk part. Because the reward is pretty clear. And it's even clearer if you're on a 1 imposter game, because if you throw out one of the imposters, your reward is you win the games. Anyway, the problem is this risk. Because I put the risk as 1/6 of the crew, but let's say that we're later in the round, okay, and a bunch more people have been killed. So let's see, 2 imposters, let's just say 2 more people have been killed. So now there's 6 people in total, right? There are 4 crew instead of the 6. So, and there are 2 imposters. And this is one of those scenarios where you have to vote, right? Because if you don't, then the imposters will double kill. So you could say, okay, the risk is now, well, the risk is a little higher. It's now 1/4, but the reward is still 1/2. And if you plug these numbers in, you will get 1/3, if I'm not mistaken. But the details don't matter. You'll get something relatively low. Most of the time this yields a pretty low result, right? So you only have to be 33% sure of one of these guys here, one of these remainders, being an imposter. But the problem is that now your risk is not 1/4, your risk is actually losing the game. So it should account for the fact that if you vote wrong, you instantly lose the game. And so, and this factor should also be accounted for when we have more crews remaining, because obviously it's not as big as an impact, but it still matters. The imposters could still get a couple double kills and win the game after one round of voting. So this simple break-even formula doesn't take that into account, and because of that, it's flawed, making it seem that voting is the right play basically every time, even though sometimes it isn't, which leads us to the next part. So let's consider a scenario over here where there are 2 imposters left and there are 5 crewmates. So the first, by the way, assumption of this decision tree is that we're going to vote every single time. That we're in a meeting, we're going to say, okay, at the end of this meeting, crew is going to vote together. Okay. So after they voted, there are obviously 2 options. Either they vote correctly or they vote incorrectly. If they vote correctly, then obviously one of the imposters is going to, get thrown out or whatever, and so the total amount of imposters will decrease. If they vote incorrectly, the crew will decrease. And so you'll notice here that the amount of crew is less than or equal to twice the amount of imposters. And so this means that the imposters, theoretically, because the round starts over after voting, could get a double kill. They theoretically should always be able to get a double kill, sealing the deal and losing the game for a crew. So, and that's why you often hear people say, don't vote on 7, or 2 imposters, 5 crew, because if you vote wrong, boom, the game is over. On the other hand, if you vote correctly, you now are left with 1 imposter. And you play the game, whatever. And again, this is just assuming that no kills happen. This is all theoretical, so that's another assumption and flaw is a better word, of this decision tree. But okay, so let's say you get to the next meeting, everybody's alive, or you just immediately call a meeting. If you vote again, you get rid of all the imposters, and that results in a win. If after you vote again, you don't win, meaning that you voted incorrectly, well, you result with 1 less crew. So, and then in this case, we vote wrong, there's 1 imposter left, there's 4 crew, and the cycle just keeps repeating on until we either get a win or a loss. Now, for this to make mathematical sense, what we're going to do is we're going to assign values to these results. So a loss is going to be -1, and a win is going to be +1. And so how are we going to evaluate the expected value of each, of each position right over here, is by evaluating the position over here and over here and taking an average of them. But what I did is I wrote a little Python program to simulate this and calculate the expected value.